All right, so in this module, we've already done some examples, me doing them first. So now I want to give you a chance to work on some first before we go through them. So I've got a thorough list here of defects that we want to describe by Kroger-Vink notation. So there's 11. So I don't mean for you to do all 11. You can if you want. But the idea is pick at least one. In the quiz, you'll see further instructions, but try to answer that before we go through the work here in a second. So basically, choose one of them, and if you already know one, maybe challenge yourself and do something further down the list as they get more difficult. So pick one or do multiple. Do as many as you want, but in the quiz it'll have you do at least one, and then come back and we're going to kind of go through them one by one, a little bit more rapid fire than we did in the previous module. But I'll kind of show you what we tend to get for these defects and Kroger-Vink notation. So pause the video, come back, and we will work through these notations. All right, so you've had a chance to at least do a couple of these. So let's go through and work these kind of one by one. So I apologize if the wording is confusing on these. It says for the first one, it said cation substitution during potassium chloride for sodium chloride. What I'm trying to get at there, and if it's a little confusing, I apologize. But what it's saying is your base is this one, and you're replacing it with this. So basically, the first thing replaces the second thing. So that's for all of those. I apologize if that was confusing. So let's go through that. So we're in this case, the species then, if we're dealing with a cation substitution, then this is our species, so potassium, and it's replacing, if it's a substitution, the sodium, and then we deal with the charge. So charge on both of these is +1, so there's not going to be any difference in charge, but if I want to just write that out, I'm going to subtract the +1 of sodium and add in the +1 of potassium. So that's no charge or null for that. All right, so that's how we write that one. All right, so then we add in this for this. And so in this case, it's talking about anion substitution. So we're referring to this is our species, so fluoride. It's taking, if it's a substitution, it's going to take the place of the other anion, so oxygen. And here, if we subtract the -2 of oxygen and add in the -1 of fluoride, then that would give us what? +2 -1, so +1 charge, and that would be a single dot. Okay, so we've got this so far. All right, so cation substitution, magnesium oxide for aluminum oxide. All right, so this again, if we're talking about the cation, is our species, Mg. And then if it's a substitution, it's going to take a similar cation spot, so Al. And then again, we do the charge, so we're moving the, in this case, it's +3 for aluminum, and adding the +2. And I'm just getting that because the charge of oxygen is fixed at -2, and so that's why we can know the valence of some of these. So you can also look at some of the tables in the book if you're unclear about the charges as well. Okay, so that's a -3 +2, so -1, and so we have a single dash here. All right, the next example, it just wanted us to do an oxygen vacancy. And I put these with oxygen, so oxygen vacancy and then oxygen interstitial for 5. I put these in there because we're going to, in the next sections, talk a lot about oxides. And so you're going to see these a lot, and so it might just be useful to memorize what these two look like. So oxygen vacancy, the species here is the vacancy, not the oxygen, right? Because we're talking about the vacancy, so there's no oxygen there. And so we have V, but it is in the oxygen site, so O. And then the charge, we're eliminating a -2 charge, so this is going to be a +2 charge, so double dot. All right, so this is oxygen vacancy. We've got that one from previous. So now we want to look at oxygen interstitial. Here, oxygen is the species because the interstitial refers to the site. And so we put that down here. And then we're adding that -2 charge. And so this is going to be a -2. And so it's double dash in this case. All right. Now we're looking at zinc oxide. So a cation vacancy in zinc oxide. This is my cation, but the vacancy is the actual species. And so it's a vacancy on the zinc site. And then again, we subtract, in this case it's +2. So this is going to be a -2 charge because we have a -2 charge if we remove a +2. All right. And then the last one for this page, and then we'll move on to the next page, is going to be cation interstitial. So zinc is the cation. It's going into the interstitial site, so position. And then we're going to add that +2, so that's going to be a double dot. All right, so on to number 8, which is an anion substitution. And again, we're substituting this into this compound. And so the anions, we're talking about these two. And this is the species that's getting added. And so this is going to be sulfur, and it's replacing oxygen or substituting oxygen. And so to balance that charge, we remove the oxygen, -2, and add the sulfur, -2. So in this case, they're both the same charge, and so that should work out to 0. All right, so now let's look at interstitial and zinc sulfide, and it's the anion. So we are talking about the sulfur here. That's the anion, and it's going into the interstitial site, and we're adding that -2 charge. So this is going to be a -2, and so double dash here to represent that. All right, so the last two are meant to be a little bit more challenging and not exactly like the others. But we can still describe them by Kroger-Vink notation, and they're still what we would refer to as defects. So, but again, they're a little bit more complicated. So here we're looking at a reduction of the cation in Fe2O3. So it's not super clear here, but Fe2O3 to divalent. So a reduction implies a change in the oxidation state, right? And so divalent is talking about +2. And if we work out this, oxygen is 2-, so that means -6 charge divided by 2, and that gives me a +3. So our reduction is from the perfect crystal, which is +3, to +2. So it may seem like we're just changing the valence here, right? And we are, but we can also write this out in the form of Kroger-Vink notation. And the way we approach this is by, we have Fe3 plus, and we basically say we're substituting it with an iron 2 plus. So we go from Fe3 plus to Fe2 plus. So we can write it just like the substitution up here. And so that's what we're going to do. So we have an iron, Fe, and it's going to go in the iron site. But the important thing is the charge, right? So we start with the 0 charge, we remove the +3, and then we add back the +2. So this would give us a -1 charge. And so we have a single dash, right? So it's just like saying we're going from an Fe3 plus to an Fe 2 plus. So even though there might not be a substitution, we can write it like that in order to describe it in our Kroger-Vink notation. So this is how we would describe it. All right, so again, approach it like a substitution. So this last one is then talking about an oxidation. So basically the opposite direction as the reduction, but we're still talking about a cation, in this case manganese, and a compound LiMn2O4. So let's just look at the charge real quick. So again, 2 minus. This is going to be 8 minus. Lithium is always plus 1. So if we do that, this is minus 8. Subtracted this, we're left with 7. So the 2 manganese have to have a 7 charge. So if we divide it by that, right, it's 3.5. So what that tells us is that we actually have both 3 and 4. So we actually have plus 3, plus 4 charges. And so if our reduction is going from 3 plus to 2 plus, here our oxidation would be to go from Mn 3 plus up to Mn 4 plus. Right? So we can approach it in the same way, a substitution of manganese, but different charges. So in this case, 3 to 4, right? Because the charge only balances out if we have a 3 and a 4. So this then would look like Mn for an Mn, right? It's going into the same site. And then if we remove that plus 3 and add the plus 4, it should give us the opposite charge here, right? And so sure enough, minus 3 plus 4 plus 1 charge, and so that's a single dot, right? So we can approach these just like we did substitutions, even if we're talking about reductions and oxidation. So that's an important thing to keep in mind when you're looking at different defect structures. Like you can talk about reductions and oxidations in the same manner.